Write 60 as a product of prime factors. Now what on earth does that mean? Now it doesn't really make much sense. It is a standard type question, write something as a product of prime factors, and we can unpick this a little bit by looking at some of the individual words and phrases in the question, but it isn't going to make a lot of sense as a question until we've done it. So what we'll do, we'll unpick it a little bit, try and get some clues to what we might be needing to do. Then we'll do an example, we'll do this question as an example, and once we've got to the answer, we'll be able to link it back to the question and explain how the question is asking us to do that. So, clues we've got. Well, clearly it's something to do with this number 60. 60 is going to be involved, and in fact 60 is going to be our starting point. Whenever questions start with write, the suggestion is write 60 as something, suggests that we're going to take 60. We're still going to have 60 at the end, but it might look a little bit different. We're going to do something with the 60 and we're going to rewrite it in a different way. So when we say write, we often mean kind of rewrite, as in change. Take 60, change it a bit, so it still is 60. Whatever we end up with is still equal to 60, but it looks a bit different. It's written in a different form. Rewrite in a different. But what different form? Well, that's the question. So we'll have a look at some other clues in this question, because there are a few others here. We've got a mention of prime factors. Now we know about this word prime, and we know about these things, factors. So prime numbers. Well, we know about prime numbers, we know about factors. Prime numbers. Any number is a prime number if it has exactly two different factors, and those factors are 1 and the number itself. So clearly there's going to be something involving prime numbers here. And we've got this word factors. Now factors, remember, are things that something will divide by. The questions in the times table that we could use to make up a particular number. Now if we're talking about 60, perhaps it's something to do with factors of 60. And perhaps it's something to do with prime numbers as well. So maybe it's something to do with those factors of 60 that are prime numbers. If we wrote out the factors of 60, some of those factors would be prime numbers and some of them would not be. So maybe it's something to do with the factors of 60, and maybe it's something to do with prime numbers. And we've also got finally one more clue in this question, and that one more clue is this word product. Now product is a fancy word for one of the basic operations that we can do with numbers. You may know, you may not know, but if we talk about the product of two numbers, what we mean is we mean times. Product is a fancy word for times. So we still don't have many clues, we still don't have much of an idea what this question is asking us to do, but clearly it's something to do with 60. It's probably something to do with factors of 60, something to do with those factors which are prime numbers, and something to do with times. So what we'll do now is we'll run through the method for these questions. All of these questions have exactly the same method, just with a different start number. We'll run through the method, we'll reach an answer, and when we've reached the answer, we'll link it back to the question and see where the answer came from. So whenever we've got one of these questions, write something as a product of prime factors, we always go about these in exactly the same way. So we're going to start with the 60. And what I'm going to do is I'm going to have two branches coming off the 60. And at the end of these two lines, I am going to write down two numbers, any two numbers that times together to make 60, with the exception that I can't write down 1. I can write down any two numbers that times together to make 60. There are lots of different options for this. I'm going to choose 2 and 30. They have to be a pair, but any pair will do. I'm going to look at the 2 first of all. Is 2 a prime number? Well, yes it is. It was on our list. The only thing we could split it into a 1 and 2. We're not allowed to do that because we're not allowed to use 1s in this question. 2 is a prime number. Once I hit a prime number on a branch, that's these lines, then I can't do anything else on that. So I'm just going to circle that because that is done. Dealt with. Finished. Now on the other side, is 30 a prime number, or could we split it again? We can split it again. So what I'm going to do is I'm going to have 2 more branches coming out of the 30, and I'm going to write down 2 numbers that times together to make 30. Any 2, with the exception that I can't use 1. So I could write down, say, 2 and 15, or I could write down 3 and 10, or I could write down 6 and 5. It genuinely doesn't matter which pair you do. I'm going to go for 3 and 10. I will prove in a bit why it doesn't matter which pair you do, but I'm going to go for 3 and 10. Is 3 a prime number? Yes, it is. So I can circle it. There is nothing more that I can do. I'm aiming for prime numbers at the end of these branches. Is 10? No, it isn't, because we could split 10 into, for example, 2 and 5, because 2 times 5 is 10. 2 is a prime number, so I can circle it, and 5 is a prime number, so I can circle it. I have nothing else at the end of branches that is uncircled. So what I've done is I've started with the 60, and through this kind of, almost like growing a tree, I've branched out into different bits, 2 numbers that times together to make the one we're branching off from, not using 1 at any point, circle it if it's prime, leave it if it isn't. Final thing I have to do, I now need to have 60 equals. I take these numbers in the circles. They are all, first of all, notice, prime numbers. 2, 3, 2 and 5. Of course they are, because we wouldn't have circled them if they weren't. What I'm going to do is I'm going to write these out at the end. I'm going to put them in size order. You don't have to. You can have them in any order you like. You can have them as 2, 3, 2 and 5. I'm going to reorder them and put them in size order. 2, 2, 3 and 5. And all I'm going to do is I'm going to put times signs in between them. Why? Because what is 2 times 2 times 3 times 5? Well, 2 times 2 is 4. Times 3 would be 12. Times 5 would be 60. So what I've done is I have broken 60 down into some numbers that times together to make 60. Each of these numbers is a prime number. So, think back to that question. Write 60 as a product of prime factors. Here is the 60. This is also equal to 60. So the answer, and this is the answer by the way, this 2 times 2 times 3 times 5 is the answer. This is a product of prime factors. So this is me having written 60 in a different way. It's still equal to 60. It's just written in a different way. Each of the things in here are times together, so there's the product bit. Each of these is a prime number, so there's the prime bit, and each of these, in fact, is a factor of 60. 60 will divide by 2, 60 will divide by 3, and 60 will divide by 5. So what I've done is I've written 60 as a product of prime factors. A load of prime numbers times together that gives me the number I started with. Now I mentioned just then that it didn't matter which pair of numbers you picked. Any pair of numbers that times together to make whatever you're branching off from will work. So what if at the beginning, when I had 60, I'd started with, say, 6 and 10? That would be okay because 6 times 10 is 60. Is 6 a prime number? No, it isn't. Well, we could split 6 into 2 and 3, both of which are prime. Is 10? No, it isn't. But we could split 10 into 2 and 5, both of which are prime. And you see we obtain the same 4 numbers, 2, 3, 2 and 5. Whichever pairs of numbers you chose to use, you would still get the same prime factors at the end. You might have them in a slightly different order, but you will still get the same numbers. Any number only has one product of prime factors, one way of writing it, as all those prime numbers times together at the end. It's just that the root there might be slightly different depending on which pairs you pick. Reasons why we can't pick 1, just to make this really clear, if I'd put 1 here, I couldn't circle it because it's not a prime number by definition, but I also couldn't split it up into anything. I could only split it up into 1 and 1. And we'd have to keep going in that way and it wouldn't help us. So we have to pick a pair of numbers that isn't 1. But any pair of numbers will do at any point in this because you'll get the same prime factors, the same things in the circles at the end, just in a slightly different order maybe. Now, write something as a product of prime factors, as I've said, is a standard question. You are always going to do exactly the same method, just with a different start number. And whenever you see those words, product of prime factors, one word should pop into your head, and that word is tree. Because you are going to be constructing one of these tree-like things with these branches, branching out into prime numbers. every single time you have one of these questions. It doesn't really matter if you don't quite understand the wording of the question. Just see the wording of the question as an instruction to do this tree thing. So whenever you see write something as a product of prime factors, think tree. Okay, we'll do another example just to make this point. Write 48 as a product of prime factors. So very much the same kind of question. We're going to start with 48, and we're going to split 48 along two branches into any two things that aren't 1 and 48, any two things that times together to make 48. There are lots of different options. Some are perhaps more obvious than others. If you get really stuck, if you really can't see one, things that are worth checking. It's worth checking whether it will divide by 2, because you'll make the numbers smaller fairly quickly, and it's worth checking if something will divide by 10. This one won't divide by 10, but it will divide by 2, and that's a pretty easy spot. Again though, any pair will work. You could do, say, 4 and 12. You could go for, say, 6 and 8. I'm going to go for 2 and 24 because it's an easy spot. 2 is prime, so we can circle it. We don't need to do anything else with that. We're happy with that, leaving it alone. 24, however, can be split again. And again, I could look for an easy spot like 2 and 12, or I could look for a more complicated one. I could think about whether I could make them two quite small numbers and go for something like, say, 4 and 6, maybe even 8 and 3. I'm going to go 2 and 12 again, and 2 is prime once again. 12 though, well, 12 I'm going to shake it up a bit. I'm going to go for 3 and 4, because why not? 3 is prime, and 4 we're going to split into 2 and 2. But again, whichever pairs of numbers you used, you'd still reach the same answer at the end. Final thing we need to do, and we do need to do this because this is the actual point of the question. This is just our method, and there will be marks available for this, but this is the actual point of the question. 48 equals 2 times 2 times 2 times 2 times 3. And again, I've put them into size order, smallest to largest. You don't have to, that's personal preference, but I have done here. We could always check it. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3, well, we might have to think about that one a little bit, but 16 times 3 does turn out to be 48. So what we've done is we've taken 48, we've written it as a product of prime factors. I have here the factors of 10, 1 and 10, and then 2 and 5, and the factors of 15, 1 and 15, and 3 and 5. And I've worked these lists out in the way that we did before, working in from 1 and 10, then into 2 and 5, 1 and 15, into 3 and 5, working in from both ends of the list to get a complete list. These are the complete factor lists of 10 and 15. And there are things we can notice about this. Well, first we might notice that there are certain things that the lists have in common. There's a 1 in both, and there's a 5 in both. Now, the 1 being in both is not very interesting, because actually 1 will be a factor of any number at all. But the 5 being in both is interesting. We can say that 5 is a common factor of 10 and 15, because it's common to both lists, it's in both lists. But in fact, we can say that 5 is the highest common factor. 5 is the highest common factor because in fact it's not just that it's in both lists, it's that it's the biggest thing in both lists. And if you are asked to find the highest common factor of a pair of numbers, it is no harder than list the factors of one, list the factors of the other, and then pick the biggest number in both, exactly like I've done here. Classic question here would be, write down the highest common factor of 10 and 15. So I wrote down the factors of 10, the factors of 15, and then picked the biggest number in both. You would never be asked to find the lowest common factor, only ever the highest common factor. Why would you never be asked to find the lowest common factor? Because the lowest common factor of any pair of numbers, any pair at all, would always be 1. 1 is a factor of anything at all, so the lowest common factor of any pair of numbers would always be 1, and the question is thus a bit pointless. It's not interesting. If it's always the same answer, it's not interesting. Why is highest common factor a thing? Well, you don't particularly need to know that, but there are lots of things much higher up that use highest common factor, lots of much more advanced bits of maths that use highest common factor. as a bit of a basis. But it's a really easy thing to do. If you can find factors, then you can find highest common factor. Find the lowest common multiple of 4 and 5. Similar kind of question to the factors one, really. It's just that we're talking about multiples here. So this time we are looking for multiples. So we're going to think about multiples of 4, multiples of 5, i.e. the answers to the 4 times table and the answers to the 5 times table. We are going to think about common multiples. So we're looking for numbers that turn up in both lists. There will be lots of numbers that turn up in the 4 times table as an answer and the 5 times table as an answer. But we are looking specifically for the lowest one. So if we're looking for the lowest common multiple, actually a nice quick and easy way to do it will be to just list multiples of 4, list some multiples of 5, a few at a time until we hit one that's in both lists. If you're being asked for lowest common multiple, they are expecting people to do lists. So the list will never be so long that it's not possible to do. You are going to be able to find one by listing. So we're going to list some multiples of 4 and we're going to list some multiples of 5, and we're going to look for the first thing that turns up in both lists. Well, about 5 at a time, 4 or 5 at a time is probably okay to do. So if we go 4, 8, 12, 16, and then 5, 10, 15, 20. Okay, we've not hit anything yet, but we could go 20. Oh! 20's in both, and in fact 20, the first number we hit that's in both lists, the lowest common multiple of 4 and 5 is 20. It so happens that 4 times 5 is 20. That's not always going to be the case. The two numbers multiplied together will always give you a common multiple, but it won't necessarily be the lowest. But if you need to find lowest common multiple, just list some multiples, few of each, few of one, few of the other, until you hit something that's in both lists. Why wouldn't we be asked to find the highest common multiple? Well, we'd never be asked to find the highest common multiple because there isn't one. For any common multiple, you could always just say double it, and there's another one. So we'd only ever be asked to find the lowest common multiple. The highest common multiple is not possible. So if you're asked to find the highest common factor, sometimes shortened to HCF, then all you need to do is write down the factors of one number, the factors of the other number, and look for the biggest thing that's in both lists. And if you're asked to find the lowest common multiple, often shortened to LCM, all you need to do, write down a couple of multiples of one, a couple of the other, and keep doing that, keep adding to the lists a few at a time until you hit the first thing that's in both lists, and that is your lowest common multiple. There is one final way we could find highest common factor, and we should only really use this method if we are clearly being pushed in that direction. Generally speaking, doing highest common factor and lowest common multiple as lists is the much better way of doing it. Just list the factors, look for the highest common number between both lists. But if a question is clearly pushing us in this direction, we might have to take this route. An example of a question that might do that would be something like this. Part A, write 12 as a product of prime factors. Part B, write 30 as a product of prime factors. And part C, find the highest common factor of 12 and 30. So this question is clearly pushing us down the route of using product of prime factors. And in fact, parts A and B are nothing we haven't already seen before. So part A, product of prime factors of 12. So that's the tree thing, product of prime factors, we should think tree. So we start with the 12. We're going to split the 12 into any pair of numbers that times together that doesn't include a 1. Any pair of numbers, let's have 2 and 6. 2 is prime, so we're going to circle it. 6, we could split into 2 and 3, and they're both fine. So we could circle them, because they are both prime numbers. And underneath, 12 is 2 times 2 times 3, with me putting it in numerical order. Part B then, Right, 30 is a product of prime factors, so that's the same thing again, it's the tree. 30 we're going to go into 3 and 10, where 3 is prime. 10 into 2 and 5, where they're both prime. And underneath 30 is equal to 2 times 3 times 5. Now part C, write down the highest common factor of 12 and 30. Now you could very much do this as lists, list the factors of 12, list the factors of 30, but it turns out that because we've clearly been pushed down this route of product of prime factors, it turns out that we can use these, the products of prime factors that we get at the end, to find the highest common factor. Now again, and I cannot stress this enough, I would suggest that you only use this method to find highest common factor if you are clearly being pushed in this direction. Generally speaking, stick with lists. But if a question like this one is clearly pushing you down this route of using the product of prime factors, then maybe you might want to use it. Although with this question you do have the wiggle room that you could get away with doing it as lists. But we can do this from the product of prime factors. Look at these products of prime factors at the end. 2 times 2 times 3 and 2 times 3 times 5. We don't have to worry about the trees now, the trees were just our method of getting there. We're only focusing on these two lists at the end. The 2 times 2 times 3 and the 2 times 3 times 5. And hopefully we'd notice that there are certain things in common. We might notice, for example, that there are 2's in both and that there are 3's in both. We might go even closer than that and notice that there is, in fact, a 2 times 3 here and a 2 times 3 here. Now clearly these are factors. 2 and 3 are factors of 12, 2, 3 and 5 are factors of 30. They must be because they're prime factors. The whole point of this prime factor decomposition, this product of prime factors thing, is that the numbers we get at the end are factors. But then if we're boxing this stuff off, well, 2 times 3 must be a factor because it's part of that breakdown. And 2 times 3 must be a factor here because it's part of that breakdown. What is 2 times 3? Well, 2 times 3 is 6. And it turns out that the highest common factor is 6 because there is a 6 hidden in both of the products of prime factors. There is a 6 hidden here and there's a 6 hidden here because there is a 2 times 3 in both. So we look for the bit of the product of prime factors that is common to both, all of it that's common, whether it's in a different order. It could have been that it was a 3 times 2 here, but that would be fine. It's still there. We look for the stuff that's common to both, times it up, multiply it up, and that's our highest common factor. But again, we'd only really go down this route of finding it if the question is clearly leading us in this direction. Generally speaking, lists would be better.